Hello everyone, I'm Jana, I'm your tech support today. During the tutorial, I want to introduce you to our tutor, Petar Korponaic. He's a founder and CTO at Contastica, and he will hold the hands-on quantum computer tutorial. So enjoy.
Okay, thank you. Thank you for the introduction. Let's wait a minute just to see if more attendees will join. Okay, I will share my screen. Okay. So as you know, my name is Petar Korponaic. I'm founder of Quantastica. Quantastica is quantum software startup registered in Helsinki, Finland. And what we do at Quantastica, we are focused on quantum software, and our products are programming tools for quantum computing. And our main focus is automatic design of quantum algorithms. This is what we this is our flagship product, let's say. But today on this webinar, I will show you one very simple and common quantum algorithm, so last time when I made a webinar, in this type of webinar, I show how to add two numbers on a quantum computer. But this time we will do something more complex. That was too easy, and that is not a real use of quantum computer, because quantum computer will not be used to add numbers. So we want to do something a little bit more complex, but not too complex, because I guess that audience of this presentation are people from computer science, from machine learning, from data science, and not people from quantum computing. So I don't want to I don't want to dig you with too many information and too complex mathematics and everything what is around quantum computing. So we will do something simple, and what we will build today, we will build a quantum program to find minimal eigenvalue of a Hermitian matrix. So this is what we will build today. I hope that it will be interesting enough. I was thinking maybe to show how to factor numbers on quantum computer, because this is a popular theme. You know, people are talking about some people are afraid of quantum computers to break cryptography, and it would be interesting to see how to factor number on quantum computer. But that algorithm, which is Shor's algorithm, there are other algorithms, but Shor's algorithm is most popular. This is a little bit too complex to explain for people who are outside of quantum computing, and I decided not to go with that into that direction. So today I will show you how to find minimal eigenvalue of a Hermitian matrix. And classical equivalent of this algorithm is present in many programming languages and frameworks. This is in Python. It's this EIG function, which returns eigenvalues of of a matrix and sorted. It returns eigenvalues and eigenvectors of a matrix, and we are interested into minimal eigenvalue. Now, why is this useful? First of all, to tell you that I will not explain what is eigenvalue and eigenvector. I guess that this is common knowledge, and everybody knows what is. This is basics of linear algebra, so no need to explain what is eigenvalue and eigenvector. Why this is useful? Why this minimum eigenvalue is useful? This is because energy of a system is expressed with Hamiltonian matrix, and Hamiltonian is Hermitian matrix. Now, minimum energy of a Hamiltonian is less or equal to minimal eigenvalue of a Hamiltonian matrix. So with this method, we can calculate minimum energy of a system described with Hamiltonian. So when input is Hamiltonian, output is ground state energy, or value which is at least, which is not smaller than minimum energy of a system. For example, this is used. It has broad use, and for example, one of the use is in chemistry, in computational chemistry, where energy of a molecule is expressed as a Hamiltonian matrix. It's converted into Hamiltonian matrix, and then by calculating minimum eigenvalue, we can find a minimum or ground state energy of a molecular bond, for example. And so it has a lot of use, and this is why I choose this method. This algorithm. Now, classical algorithmic complexity of eigen decomposition is n is cubic complexity. So it's this complexity is not extreme. It's not extreme. It's not exponential. It's polynomial. But for large matrices, it's hard to calculate eigenvalues on a classical computer. Now, quantum computers, quantum algorithms promise to solve this problem with less complexity. So faster than a classical computer. Of course, this is only a theory for now. In practice, quantum computer, because there is a noise present in quantum computers, it's challenging to calculate large matrices. I mean, to calculate eigenvalues for large matrices, because a noise. So this can be done only for small matrices for now, but complexity of quantum algorithm is smaller, and this is one of possible use of quantum computer in the near future, when quantum computer became fault tolerant, or not fault tolerant, but with less noise. So this is one of the promising quantum algorithms which will be in use in production, I hope soon. And so this is why I choose this algorithm. Now there is actually two common quantum algorithms to perform this calculation. One method is variational quantum eigensolver, which is hybrid quantum classical method. This method is using both quantum and classical computer in a loop, and one part of the calculation is performed on quantum computer, and other part of the calculation is performed on classical computer. So this is hybrid. This is called hybrid method, and it's very common. It's very frequently used, and you can read everywhere on the internet about this algorithm. Second method to perform this is QPE, which is quantum phase estimation algorithm. This algorithm is quantum only. It's not quantum classical. It's not hybrid. It's quantum only algorithm, and it's frequently used as a building block in other bigger quantum algorithms. So it's also frequently used, but due to complexity of implementing QPE, actually explaining how QPE works, I decided to go with VQE. Actually, my idea was to do both on this presentation, but I don't think that we can cover both algorithms on this one presentation, and maybe it will be too much to cover both. So we will go with this VQE quantum algorithm. Why? So I said this is because VQE is relatively simple to implement. It's maybe one of the simplest quantum algorithms to explain, because only one small part of the calculation is performed on quantum computer, and the rest is performed on classical computer. So it will be not too hard for audience outside of quantum computing, how to say, to understand. And and also it's because this is the data science conference and people our audience is familiar with machine learning and this algorithm is using techniques which are common in machine learning. So it's perfect match for this conference. Now let's see. Before we start, let's talk about a little bit theory. So eigenvalues of a Hermitian matrix are real numbers. Even if Hermitian matrix is complex matrix with complex elements, eigenvalues are real numbers. This is mathematical property of a Hermitian matrix. Now, eigenvectors of a Hermitian matrix are unit vectors. That means that sum of squares of elements equals to 1. Sum of elements of eigenvector equals 1. And this is important. Why this is important? Because state of a quantum computer can be described with unit vector, with complex unit vector. So state or wave function of a quantum computer, of a quantum system, which is in our case, this is quantum computer, can be described with a unit vector. Now it's perfect. So you can see this is perfect match because we have eigenvectors which are unit vectors, and we have state of quantum computer which is unit vector. Also, the eigenvectors are complex, can be complex, can have complex elements. And also state of a quantum computer is a complex unit vector. So this makes storing eigenvectors in a quantum computer relatively easy, because we don't need to encode we don't need to perform complex encoding. We can it's relatively easy, I mean, to store. So this is perfect match for quantum computer. And now expectation value is calculated this with this method. I will explain what is this. I explain what is this. So when we multiply vector with Hamiltonian and then multiply that with conjugate transpose of a vector, we get the expectation value, which is average energy of a system, and is in ideal case it is equal to eigenvalue or ground state energy of a system. So so this is I will explain what this means. And what we are searching for, minimal expectation value. So we are searching for vector or state of a quantum computer which multiplied with Hamiltonian, with input Hermitian matrix. I'm not talking about Hamiltonians now. I'm talking about Hermitian matrices. So which will give us the minimal expectation value, which should be eigenvalue of a matrix, of an input matrix. Okay, so now to explain this, this notation is used in quantum, mostly in quantum physics. and this is bracket. This is named bracket notation, and or Dirac. So it came from physicist Dirac, and this notation is very common in quantum computing. Outside of quantum computing, is maybe not that frequent. And what that means? This part, this right part, is named cat, and it represents a column vector. So this is column vector of vector in how to say vertical direction. So this is column vector, and this left part is named bra, and it's row vector. So the same vector, but transposed in a row, and not only transposed, it's conjugate transpose of this vector. And H is our Hermitian matrix, and this means matrix H multiplied with vector psi, and then multiplied with conjugate transpose of a vector psi, and result is scalar, because we are multiplying. We are multiplying matrix with a column vector. Result is column vector, and then we multiply the row vector with column vector, and result is scalar. And this scalar is expectation value of our expectation value. And in Python, we can write it as this way. And now I hope that this is that everybody understands what I'm talking. It would be better if I have feedback, but now I feel like performing monologue. But okay, let's see. Let's continue. So let's get back to VQE algorithm. Now it's important to explain what is quantum computing actually doing. What is quantum computing performing? Not only in this algorithm, but generally. Quantum computer always starts from a zero state. So before any computation, quantum computer is reset to zero state. This is vector, which can be described as a vector with first element 1 of 1, and all other elements are 0. So this is zero state, and this is a state in which we start any calculation on quantum computer. Now, because quantum computer doesn't have input port, we cannot directly write data into quantum computer. We cannot reach that state of a quantum computer. That state is actually not how to say. It's not a memory like classical computer. That state is we only describe state of a quantum computer as a vector, but this is actually probabilities. It represents probabilities of measuring state in measuring quantum computer in some of the possible states. So there is no way to write into quantum computer, and when we want to enter some information into quantum computer, we need to perform a quantum program which will transform this zero state into our desired state, into state where we have data encoded. So this is how quantum computer works. And now program of a quantum computer, quantum program, can be described as a unitary matrix. So state of a quantum computer can be described as a vector, and quantum program can be described as a matrix. And what quantum computer performs after executing quantum program, we have a new state or final state of a quantum computer, and result of executing quantum program is equivalent to multiplying initial state with unitary matrix. And this is actually all that quantum computer can do. So quantum computer cannot do anything else. I'm talking about gate-based universal quantum computers. So quantum computer cannot do anything else. Quantum computer can only the execution of a quantum program is just a multiplying state which is unit vector with unitary matrix, and result is new unit vector. So quantum state is always unit vector, and this is what quantum computer can do. And also we cannot directly read from quantum state. So people who are coming from classical computer science can see how this could be difficult, because we cannot write into our computer, and also we cannot read out of our computer. So this is very difficult. We cannot read. We cannot directly access this state, the state of a quantum computer. We can only sample out of it. So we can only read and we also cannot directly read elements of a vector. We can only read the index of a most probable outcome of a vector, of this vector. So measuring or reading out of quantum computer is called measurement, and this is even more complex or even more computationally expensive than writing into quantum computer, because we can write, we can enter information into quantum computer by performing quantum program, but to read out of quantum computer, we can only sample out of it, which is problem. So if we want to get the entire state vector, all values of a vector, to reconstruct the state of a quantum computer, this is computationally expensive, and this is one of the showstoppers, how to say, from reaching quantum advantage, because in many algorithms, when quantum state becomes large, it's hard to get precise data out of quantum computer. But okay, these are problems, and we are dealing with that. I need also for you to understand that this is not an engineering limitation. This is this is fundamental property of a quantum physics. This problem will never be solved. This is not something that we don't know how to do. This is something that is impossible to do. So we cannot reach the quantum state directly. We can only indirectly reconstruct the quantum state, and this will be like that forever. And this is why quantum programs and quantum algorithms are designed in a way that we don't need entire state vector, because state vector could be very large. State vector of, for example, of 180 qubit quantum computer, state vector is 2 power 180. And this is extremely large number. This number is in range of number of atoms in the universe. So reading that vector doesn't make sense. And I mean, we also don't have where to store that vector. So we are not reading directly reading vector from quantum computer. But in this case, for this algorithm, we need to read a vector of a quantum computer because we are interested into this value, because we want to calculate cost of I mean expectation value, and in order to calculate expectation value we need to have a vector. And this is challenging part of this algorithm, but that's life. So now I moved to this right side. So what we do, we initialize quantum computer into 0 state, and we initialize a quantum program to some initial state, and then this quantum program is parameterized. What that means? That means that we can, when we change these parameters, here marked with shown with symbol with theta symbol. By changing these parameters, we are actually changing matrix, unitary matrix so we are changing quantum program, and this quantum program, the goal in variational or hybrid quantum classical algorithms where this method is used, the goal is to choose a quantum program to be as short as possible, but in the same time to have possibility to take any by changing parameters to make any unitary transformation. So in ideal case it would be universal quantum circuit, which means that by changing parameters we can make any unitary matrix of this dimension, but as number of qubits or when size of a matrix gets larger, that universal quantum program, which will take any unitary matrix, is large, and the number of parameters would be very large. So this is not possible, and one of the challenges with this algorithm is to choose optimal transformation, optimal quantum program with as less as possible number of parameters. And also it's important to choose a good initial state, because when we have good initial state close to I mean something closer to output, then we have less iteration. But let me continue. We initialize quantum computer in 0 state. We initialize a quantum program with some zero, for example, 0 parameters, random parameters, or if we have smart algorithm, we have some smart initial state, some smart selection of parameters. Then we multiply. So quantum computer executes, produces the final state, which we read. classical computer, and now in this right part classical computer is performing. It calculates the expectation value, which is cost of objective function, and classical optimizer, everybody here understand what is optimizer. So classical optimizer takes cost and updates parameters of quantum program, which then takes another unitary transformation. So now we have our unitary matrix is slightly changed because optimizer changed parameters, and then we execute again. We reset quantum computer to zero state. We multiply now with new matrix. We get new final state. Then we have new cost, which is hopefully less than previous value. Then optimizer takes that, optimizes the parameters, and so on. And this loop executes multiple times. The bigger is vector of the bigger is our problem. The bigger is this Hamiltonian. The more iterations we have. But as I says, the goal is to somehow make smart choice of this program to make less iterations and to reach the solution faster. Now, when optimizer reaches minimum value, that minimum value, this cost, will be expectation value of a Hamiltonian. So and this is our solution. So this solution is in our classical computer. So we simply, when this converts, this cost is our output, and we have a solution. Now this is how VQE works. I hope that this is understandable. I mean, as I said, I don't have feedback. Let me see. I'm not good with this. Let me see in the chat. Please comment in the chat. I mean, I will continue, but before I continue, let me see in the chat if something is not understandable. Please write into chat. If you don't understand something, if I need to clarify something, explain in more details or something, please write. Please write into chat. No comments, okay. Then let me continue. Okay, now I'm doing this almost ad hoc. So now what? One important thing to say is that quantum computer cannot execute arbitrary unitary matrix. Quantum computer can execute only a small set of unitary matrices, which are called gates. So in gate-based quantum computers, this is called gates. So operation of instruction of a quantum computer is gate. Is called gate, and operation of a quantum computer is actually a matrix. So we have only small set of matrices. I will open Quantum Programming Studio, which is our Fantastica's homemade tool for designing quantum algorithms, and I will put one quantum gate to the circuit. So what is quantum circuit? Maybe I'm explaining too much, but so what is quantum? Quantum circuit is actually a set of quantum operations, or quantum circuit is quantum program, which consists of multiple matrices, but it's handy to write it in a form of a circuit. It's more readable, because we are in classical computing. We have instructions of a classical computer, and those instructions are relatively intuitive for a human. But quantum program is a list of matrices, and if we deal with matrices, with hundreds or thousands of matrices, we will get lost. This is impossible for a human to follow, and because that quantum program is written as usually written. I mean, of course, you can write quantum program in Python, but you are adding matrices, so it's much easier to see and to follow what is quantum program doing by writing it as a circuit. And this is how one circuit looks like. I will make one like some QFT or something, just to show you how quantum. So this is one simple quantum circuit. So these boxes here are actually matrices, and these horizontal lines are qubits of a quantum computer. And quantum program starts from first. It's initialized to 0 state, and it starts from first gate, and it executes from top to bottom, left to right. So this matrix will be executed first, and when I select the gate, I will see it's unitary, it's matrix. This is Hadamard, and those matrices have names. These short names, these letters here, these are actually names of a matrices. So quantum program is just a list of matrices. Every matrix have a name, and people who are programming quantum computers understand what those matrices are doing, and how and understand that names, that letters. So letter H is Hadamard, and so this gate will be executed first. So this matrix will be executed first, then this one, and this one, and this one, and so on. But now I said that we need our program to be parameterized. That means we want to change parameters to make different unitary transformations, to produce different unitary matrices, and we can do that. So quantum gates are usually parameterized. So typical quantum computer instruction set of typical quantum computer is for example, one single qubit gate, which is 2 by 2 matrix, which has 3 parameters, and those parameters. So this is matrix, but this is not fixed matrix. For example, this one, or for example this one, this matrix is fixed. So this is not gate or X gate. this is fixed matrix, but this matrix has parameters. Those parameters are shown here in the bottom, and by changing parameters, those three parameters, for example, we put something like pi or any arbitrary value, we change this matrix. Now, because theta is pi, this is so cosinus theta divided by 2 and so on. So our resulting matrix will be different. By changing these parameters, we are changing actually this unitary matrix. And but this is a single qubit, so this is a 2 by 2 matrix. But our Hamiltonian, for which we are making a program, our Hamiltonian is usually bigger than, so it doesn't have only 2 elements, because that would be trivial to solve. So our Hamiltonian, our Hamiltonian here is larger, and so is our vector, and of course our program need to have the same dimension as a vector. So to make a larger matrix, and not only 2 by 2 matrix, we put these gates on multiple qubits. So we have multiple qubits, and the result is bigger matrix. And I will make this is called variational form. So this I will make one variational form, for example, of 3 qubits, and okay, and this is how it looks like. So we have single qubit gates, which in this case these gates have only one parameter. So we have, for example, two gates with single parameter gates, single qubit, single parameter gates, and we have these entangling gates. In this case, this gate is C0, but this is not important. I will not get into deepness of this, but it's important for you to understand that these boxes here are symbols for matrices, and those matrices have parameters, and changing these parameters will change the matrix of a gate, and the tensor product and tensor and dot product, depending on where is the gate here on this in a circuit. The product of all these matrices is our big matrix here. And if I turn this quantum classical, so this is hybrid quantum classical, if I turn this, then it becomes more, how to say, more visually understandable. Maybe let me clear this and make a smaller 2 qubit, like 2 qubit smaller, and I will turn quantum classical. Now we see, so we have a cost function. So this is cost function, and we have optimizer, and the optimizer updates these parameters for every gate in a quantum circuit. And when optimizer gives new parameters, the resulting the equivalent of this whole circuit will be different unitary matrix. And then when quantum computer executes, it's measured. What we measure, cost function takes outcome of a quantum program, calculates again cost, and so on. This is how it works. Now, to avoid manual work, there is a wizard here. But before that, let me show you. I made one small Jupyter notebook in which I made first a random Hermitian matrix. So this function returns random Hermitian matrix of size n. And here you can choose, do you want complex or real matrix? And let's say that matrix size is 4, so 4 by 4 Hermitian. We create that matrix, we calculate eigenvalues and eigenvectors, and using the classical method, just to for us to be illustrative, to see and to compare result of a quantum algorithm with this with classical solution. And we print that, and let's see. So this is classical. This is not quantum. So let's see how it looks classical. So I will execute this and this one. And now we have. So this is one random Hermitian matrix, and we have a list of eigenvalues and eigenvectors of this matrix. So this is one eigenvalue and corresponding eigenvector. It's sorted from minimal to maximal. So -3 is our minimal eigenvalue of this matrix. Now we want to make quantum program to calculate the same. Let me do it. So I will copy this. I will copy this matrix, this random matrix, into, and in Quantum Programming Studio we will use wizard. There is a wizard, VQE, Variational Quantum Eigensolver. So, and we will copy paste this matrix. I will explain what this wizard is doing, but I just want to avoid a lot of typing and clicking around. So I put I put this Hermitian matrix here, and I create variational form, and I choose optimization method. Only these 3 methods are currently implemented in Quantum Programming Studio because it's Quantum Programming Studio is running executing in JavaScript, and in JavaScript there is a very small set of optimizers, and so we have only these few. But you can export this to Python. You can export this to other programming language and change optimizer there. I will use this Nelder-Mead optimizer, and okay, and now the wizard made a quantum circuit because our matrix is 4 by 4 matrix. So this is dimension of matrix is 4, and this is why we have 2 qubits. Why? Because quantum state has 2 on n, so 2 power n elements, and because we have 4 elements, we need 2 qubits because 2 power 2 is 4. You know, so this is why we have a 2 qubit circuit. So this is 2 qubits, and this third horizontal line is classical register. This is where we store the result of a final state of a quantum computer. We store that in a classical register. So this third line is classical register, and we have Q0 and Q1. This is 2 qubits. We have this how much? 4, 8, 16, 16 gates. And thus we have 16 parameters. Because each gate has a single parameter, we have 16, 16 parameters. And there is a cost function. Now let's see how this cost function looks like. I will click on it, open it, and see the code. So this is the code. This is our Hamiltonian. This is the one I copy pasted from this notebook. This is that random Hamiltonian. Let's see if it is 1.53. Yes, it is. So this is that Hamiltonian, and we calculate cost, which is expectation value. So we calculate this, expectation value as I explained earlier. And we execute that until it converts, until we reach minimum. So yes. Now because quantum, because this is executing directly in browser. Later I will export it to Python, but before that. I'm using this visual tool because it's more understandable, I guess. Because this is executing in browser, this cost function, there are two cost functions. We have a Python cost function, and we have JavaScript cost function. This is absolutely the same thing, but only in two languages. So this is in JavaScript, this is in Python. We don't need both. If we want to run in browser, we need JavaScript function. If we want to run in Python, if we want to export to Python or to run this in Python program or Jupyter Notebook or whatever, then we need to write Python objective function in Python. This is automatically done by this wizard. So we don't need to type anything. So we already have, we are all set. We are full set. I am only showing you what we have. And here, when I click on optimizer, I can choose the optimizer and the tolerance of optimizer. And so let's execute this. I will go to this simulate page. And so we can see objective function. We can see the parameters. Initial parameters are now 0. There is no smart choice of initial parameters when Wizard makes this circuit. It resets all parameters to 0, and that's it. And I will click simulate, and it is running, and we can see that loss or minimum value of objective function is minus 3.08. And let's see in our Jupyter Notebook what is the minimum eigenvalue. Minimum eigenvalue is minus 3.08. So this is, let's me, 0.8036, 0.8035. Okay, so we are close because, this is tolerance. Okay, so this is how it works. And now we have parameters. So optimizer found parameters for our quantum gates. So each gate has its parameter now calculated, and result of running. So what we have? So we found this unitary. We found parameters which produce unitary matrix, which multiplied with 0 state gives us the eigenvector of eigenvector which is eigenvector of minimum eigenvalue of this Hamiltonian. And let's check that. Let's check that. So let's see. Okay, we see that we already have minus 3.08. We have minimum eigenvalue. But let's see if state of a quantum computer is equal to minimum eigenvector. So with this eigenvector. Of course, on real quantum computer, we cannot reach quantum state, so we cannot see that. But here we are running on a simulator. So this is running on a simulator, and the simulator can show us, of course, internals, and we can see the state. We can see the state vector. Let's see the state. So state is. Let's go to this simulate page where we have, and I will turn off this quantum classical. So I will remove optimizer and everything. So only the circuit will stay. So now we don't have, I mean, this way. So we don't have optimizer and cost function. We have only quantum program now. And let's see. So let's see if what is the vector. So vector is 0.18. It is not equal. I guess that, well, because we have a global phase. So this is actually rotated. So we have phase of each element of a vector. So it's not. This is why it doesn't. We cannot recognize it. But yes, we have accurate value. So that's it. This is what I want to. I wish to check this, but now if you remove global phase, you see that this imaginary part is 0, and in our case, imaginary part is non-zero. But this is only so the absolute value of this is actually the same. Is the same as this real part here. So that's it. Because in state of a quantum computer, we have global phase which we ignore, but important is that we have accurate value. We can check this. So let's generate new matrix which has different minimum eigenvalue. I will copy paste this matrix, this Hamiltonian. I will paste it into clear this one wizard VQE. I will repeat the same process again, but with different matrix. And let's see. Simulate minus 2.46. Minus 2.46. So we have it works. It works. Now we made a lot of gymnastics to make this works. In Python you can write only one line of code. Let me see, where is it? Yes, so all you need is this, but on quantum computer it's not that easy. Of course, in quantum frameworks like Qiskit and other quantum frameworks, usually there is a VQE subroutine. So you only need to call one function in Python, which will take Hamilton, which will take a matrix, and and it will execute, and you decide on which quantum processing unit, on which backend to execute. It will execute, perform everything, and return the result. So there is a function. For example, in Qiskit there is VQE function, but I didn't want to show you one line of code and go home. So I wish to for this audience to understand how quantum program works internally, and I mean, we want to learn something, not to execute a single function from framework. Now, this is not end of our troubles. So we have this eigenvalue, but we are running all this on simulator, and simulator has access. Simulator has access to this quantum state. But in real life, we don't have access to quantum state, as I already said. Maybe I am repeating myself too much. We don't have access to quantum state. We can only reconstruct quantum state, and this process of reconstructing quantum state from sampling is called tomography, quantum state tomography. And how that works? That works by measuring, by sampling quantum sampling state, then rotating this vector, and then again sampling, and then using some mathematical operations, we reconstruct some approximation of this psi, this vector. To perform that, I mean, to perform that line by line, to explain you how that works, it will go out of this presentation. It will take a long time. Maybe it will be too complicated. But it's good to know that on real quantum computer, we don't have access to state vector, and we need to perform state tomography. Now, because we are here, we are dealing with arbitrary Hermitian matrix. That means any Hermitian matrix can be input to our function. I show you this. I generated random Hermitian matrix, so anything goes in. But usually, especially in chemical applications, we get Hermitian. We get our matrix. We don't get Hermitian. For example, computational chemists will not give you Hermitian matrix. The computational chemist will give you Pauli strings, which is decomposition of a Hamiltonian. It's decomposition of a Hamiltonian in Pauli basis, so set of Pauli matrices, and I can show you that. And of course, why I am telling you this, because when you have Pauli strings, it's easier to reconstruct the state vector. Because when you have Pauli strings, then you know in which basis to measure output. I mean, to measure output of a quantum computer, final state of a quantum computer, and then you have coefficients, and it's relatively. I mean, it's easier to reconstruct this, to calculate this expectation value. But because we are now we are heroes. We want to implement arbitrary Hermitian matrix, not only Hamiltonian expressed in a Pauli matrices. Of course, we can decompose that Hamiltonian into Pauli matrices, but let's talk about what we will do if we don't have the decomposition of a matrix in a Pauli basis, in a Pauli decomposition. So what we do then, there is in quantum frameworks there is a function called state tomography. For example, Qiskit has that, and every quantum framework has the similar function, which will perform our state tomography, which will actually reconstruct state of a quantum computer from measurement by measuring, by sampling. It will reconstruct a state, and then we use that. I commented this here. We call that we pass the quantum circuit already parameterized. With parameters already set, and then it will execute and it will give us analysis, and then we get density matrix of a quantum state and then from density matrix diagonal is our psi, our state vector, and then we use that to perform calculation. So this is not the optimal way, as I said. This part is most complex. So in VQE, the most complex part, which is I didn't even write it here on this diagram, but most complex part is how to take state of a quantum, how to find how to read state of a quantum computer, and then accurately calculate this objective function, because not only that quantum computer is noisy, but we also have sampling error, which is natural error. This is like when you drop GameCube, you need to drop it 1,000 times, and you still will not have the exact number of 1s, 2s, 3s, 4s, 5s, and 6. So this sampling error is natural. And this sampling error actually confuses our optimizer. So not only that that quantum computer is noisy, but also the method of measuring and reconstructing a quantum state is also noisy. It has this sampling error, which will then confuse optimizer. So this is, challenging to perform on large matrices, on large Hamiltonians, and to get accurate results. Sometimes we can get results which will be non-optimal. So we will not have accuracy. We will have only maybe one decimal place, or maybe even we miss by integer, but which is not, of course, not enough for chemical use in chemistry. In computational chemistry, the precision is required, and this method, if executed on real quantum computer and not on simulator, it will not give us the enough precision. And the more precision we want, the more times we need to execute this loop. So this sampling this sampling, so this sampling need to be executed many times. So with the same, so I'm not talking about main loop where we optimize parameters, but when we have one set of parameters, so one output from an optimizer, we need to execute this thousands, millions of times with the same parameters, and to sample every time to sample from state to get the cost. And the more precision we need, the more times we need to execute this. And this eats the possible quantum advantage of this algorithm. But of course, I mean, this is non-explored space, so this space is not fully explored, so there could be better methods and so on, and possible this could have practical use, but currently this method doesn't give us enough accuracy. Now I promised hands-on quantum computer. So this is the name of the presentation, hands-on quantum computer. But unfortunately, I don't have, I didn't reserve the access to quantum computer. You know, quantum computers are available in the cloud, but you need to reserve access. And so I didn't do that. But let me show you how that will work on a, well, let me show you the code at least. So from Quantum Programming Studio, I will export this. There is export page. So this circuit we will export to, and you can choose many different quantum programming frameworks. I will export to Qiskit. Why Qiskit? People criticize me. Why always Qiskit? Because Qiskit is most popular. Simply, I mean, with full respect to Google Circ and others. And all those frameworks have their advantages and disadvantages, but Qiskit is most popular. So most people who are doing quantum computing are using Qiskit. So simply, this is why I'm presenting in Qiskit. But we can use anything else if you want. I mean, we can use some Pikeville or which is Rigetti or I mean. But let's stick with Qiskit. Now we choose what backend we want. So by default, backend is a state vector simulator. But we want real quantum computer. So then I choose IBM Q. So IR is local simulator installed on my computer. But when we choose IBM Q, then this is a simulator or quantum computer hosted in a cloud, in IBM Cloud. And here we choose least busy backend, because those quantum computers are very busy. If you're not partner and paying significant subscription with IBM, especially if you're using freely available quantum computers, those quantum computers are very busy. And when you want to perform something, it will take long time. Let's try. So let's try. Why not? So let's try to execute this, and so we will execute it on least busy backend. So I will download this as a Jupyter notebook. Okay, this is Jupyter notebook. We have IBM Q. Okay, and maybe this program is not not optimal. I mean, this can be shorter and more handy, and maybe we can use differently to embed parameters, not this way, but it should work. But I'm sure that it will not So let me execute. Okay, there are some warning, but it's not problem. It's running somewhere in a cloud, in the IBM cloud. You can see that it's running, but I guess that it will take a long time to execute. I mean, it's not even running. It's somewhere in a queue waiting to execute. So next time I will ask. I will next time on next webinar next year. So next year, if we make something similar like this, if you will be interested again to listen to me, then I promise I will reserve time on real quantum computer and execute something and see how it works, to show how it works. Now, I see that time is going out. Let me finish here. Let me finish here, and let's see what questions you could have, and let me answer your questions. I'm not very familiar with this. Here are some. Here are some questions already in a chat. Okay. Andre is asking, how much does it cost to run one program in quantum computer? Is it expensive? Depending on many factors. So cloud providers usually, and before that, to say that quantum okay, so the quantum computer can be accessed via major cloud providers. So you can in AWS, Google Cloud, Microsoft Azure. There are quantum computers available, but there is also IBM Q, which was first to offer quantum computers in a cloud. There are also like IonQ Cloud, and so on. And depending on how many qubits you use, how many iterations you have, what availability you expect from the quantum computer, it can go from few cents, few USD cents to couple of hundreds of dollars. I mean, it depends on many. On many factors. So this is a question. Let me try to be shorter with my answers because time is flying. So Andre, and how much is quantum eigenvalues program, including sampling to exact faster than time? So what is the gain? What is the gain? I said at the beginning that complexity is polynomial, so it's the complexity of classical algorithms is n on power 3, so it's cubic complexity. But for this variational algorithm, it's harder to determine because it's we have quantum part and classical part, and it's harder to but it should be below. So it's there is somewhere, I don't know exactly, but it's below cubic. So it's from square to cubic, somewhere between. So a gain of this algorithm is not big. There are algorithms which have much better gain in terms of complexity. For example, if we have factorial complexity of classical algorithm and then quadratic complexity of a quantum algorithm, then this is huge gain. In this case, for these particular algorithms, gain is not big, but it's the complexity is below classical. But of course, there are challenges like this, this measurement, sampling error, and so on. So which could eat that gain, and you can end with the same or even worse. So depends on many factors. Strahinja is asking, what is your opinion on quantum computing as a threat to asymmetric cryptography, and will this be replaced with Q? Okay. My opinion, my honest opinion, is that we are far from breaking any encryption with quantum computers. Unfortunately, quantum computers are not at this moment are not a threat. What is the correct pronouncement to cryptography? And it doesn't look it will happen very soon. It will happen because it's advancing, and quantum computers are getting better and better, but we are still far from that, especially with Shor's algorithm. So Shor algorithm is not a threat at all, because largest number factor with Shor's algorithm on superconducting gate-based quantum computer is number 21. It will tell you that 3 times 7 is 21. This is with Shor, but there are other algorithms, and there are also specialized quantum machines made for factoring numbers. But even those machines are currently out of. You are not in danger, so don't worry. So not yet. And until then, I guess that cryptography, the quantum safe cryptography, will be implemented in all systems, and so I don't think that there will be doomsday, that quantum computer you will wake up and quantum computers will break all internet and encryption. That will not happen, and not happen that fast, and not that. I mean, don't worry. So it's not threat, at least not for now. Natalia is thanking me for the talk. Could you please share the Jupyter notebooks with us? Okay, of course. The organizers asked me for material. I said that I don't have material before presentation, so after presentation, because I made these Jupyter notebooks, during the presentation, I will share it, and don't worry. So it will be available. With what matrix sizes is it adequate to work in quantum computer? For example, for the task you demonstrated. Okay. Yes. What matrix size? The size of a matrix. I mean, what is optimal? There is no optimal. I mean, you can try bigger and bigger matrices and see how far it will take you. Currently, this method is not better than classical. As I said, this is due to errors in a quantum computer, and so this is not a better method yet. But you can. This is very nice demonstration of how quantum computers works and how quantum algorithms work. And now most important question, by Natalia, most important question is quantum computer already used somewhere in production? Now, some people wish you to believe that it is true, but unfortunately, quantum computers are used only experimentally, and many companies, during my presentation, in November 23. So in 2 days, I will be present physically in Belgrade. During my presentation, I will show many projects which are done with by companies, and who are companies who are providers, and what they are doing. But unfortunately, still it is not yet. We are approaching, we are getting closer and closer, but we are not there yet. So there is no quantum computer currently in operation, in use in operations. So it's used in experiments, in research and development, but not yet in operations. And that's the short question is no. Not yet, unfortunately. Goran, okay, hi, chat didn't work, but this was not a very good presentation. I'd love you. What makes a cryptographic algorithm safe to quantum computing? Time is out, but I wish to answer. I hope I can. I don't know, organizer, maybe they will cut me during during the talk. But so yes, what makes a cryptographic algorithm safe? People are thinking that factoring-based algorithms are safe for are not safe from quantum. Because there is a quantum algorithm for factoring numbers. Then people think that only that algorithms based on cryptography, on factoring, are unsafe. But this is not completely true, because there is no quantum algorithm for other types of encryption, only because nobody tried to do it. So so nobody can guarantee, nobody can give you guarantee that that algorithm will not be made for any other type of encryption. Of course, quantum computers are not good with solving any kind of problems. So quantum computers are not universal, total universal machines. There is a set of in complexity theory, there is a BQP or some set of algorithms which are potentially solvable with quantum computers, but not everything is solvable with quantum computers. That means, it means that most likely there will be quantum safe, and there are already quantum safe crypto algorithms, cryptography algorithms, but you cannot be sure which one is safe, because it's people call it safe because it's not based on factoring, on number factoring. But I mean, there is nobody tried to make algorithm for solving that. I hope this answers your question. Anonymous, are there any machine learning algorithms developed? Linear regression in quantum computing, are they faster? Yes, there are machine learning algorithms for many people solve like are trying to solve many things with quantum computer, but there is no practically faster. So there is theoretically faster, but practically due to this limitation of noise, I mean, qubit connectivity, gate fidelity, and many other limitations, and also algorithmic limitations like suboptimal compiling of quantum algorithms, and many quantum error correction and so on. And because those limitations, which are engineering limitations mostly, which are getting better and better, but currently we don't have anything faster or cheaper or more energy efficient or more accurate. Any of those we don't have yet with quantum computer, but we are approaching there, we are going there, and we are also, my company is also working into that direction, so hopefully we will be there soon. That's That's it from me. I hope that this was understandable for people outside of quantum computing, and I hope that for people from quantum computing it was not too boring or too, annoying. But next year I will be better. I promise.
All right, thank you, Peter, for this interesting tutorial, and thanks everybody for watching. The next tech tutorial will be held at 11:45 a.m. So we will be waiting for you. Thank you so much. Enjoy.
Thank you very much, and thank you for attending the event.